Hello, everyone. Welcome to my Chemistry 432 catalytic project. Uh, Today I'm going to be talking about the Monsanto process and the production of acetic acid. So we're getting right into it. A brief introduction. The Monsanto process utilizes a rhodium-based catalyst that manufactures acetic acid by the carbonylation of methanol. Also, the catalyst is a homogeneous catalyst, meaning that the catalyst is in the reaction medium and is in the same phase as the reaction medium. So let's take a look here at the catalyst structure itself. This is a rhodium metal-centered catalyst complex with two carbonyl groups and two iodine groups. The electron count here is done on the right-hand side, and it comes out to a total of 16 electrons. The structure of this catalyst also has a square planar structure. With 16 electrons and the square planar structure, it makes it a very good candidate for reactivity and potential oxidative addition reactions. I also discovered the solvent of choice, which is the N-methyl-2-pyrrolidone. This is used when storing this catalyst as well. Also here I have the molecular structure as well. And also note the -1 charge in complex. So moving along here, this is the simplified net version of the overall reaction. Hydroiodide is reacting with methanol, which in the presence of the Monsanto catalyst can produce acetic acid. This right here. This overall reaction, there are 4 steps. We have oxidative addition, and then methyl group migration, then ligand addition, and then reductive elimination. Steps B and C could be combined into the same step, but I split them up just for clarity's sake in this presentation. So this here is the overall catalytic cycle of the Monsanto process. This here below is a source that I found in my research that has a very lovely diagram as shown. And I've referenced it because my artistic ability is not nearly this nice. As I briefly mentioned in the previous slide, there are 4 steps. So steps A here, this is the initial catalyst, and it goes into these 3 different intermediates, and then you get back to the initial complex of the A form there. So now I'm going to take you through each of those steps individually. So this first step is oxidative addition. And on the left-hand side, we have that starting form. As previously showed, the initial reactants is methanol and hydroiodide. They actually react to produce methyl iodide, which is oxidatively added to the complex. This is synonymous with the mechanism of protonation of a polar solvent, and the result is the transition of the methyl group and the iodide in the transition to each other. On this next step, we have a methyl group migration. So once the oxidative addition has happened, the methyl group that is added via oxidative addition migrates to one of the 2 carbonyls present in the cis position. And so this is a 1-1 migration, allowing for the insertion to take place on this now open coordination site where the methyl group was. After this methyl migration, we have a ligand addition of a carbonyl to fill in that coordination site. Technically, this previous step of the methyl migration and the ligand addition of the carbonyl can be sort of happening simultaneously. So you have a methyl group migrating on a carbonyl inserting to make a insertion migration reaction. I broke up these 2 steps for clarity's sake because these 2 steps were shown separate on the overall catalytic cycle diagram that I showed previously. So we have here the carbonyl coming in and sort of filling in this coordination site. Now, this is the last step of the catalytic cycle here, and we have a reductive elimination taking place. One of the iodines will migrate over to the acyl ligand, and it will cause that entire ligand to sort of come off through reductive elimination. And when that ligand comes off, we are left with the complex here. Believe it or not, this complex is actually now the starting form at the beginning of the catalyst cycle. And so this will now go and react with methyl iodide again and start that new catalyst cycle with oxidative addition, as I've outlined in the first step. So that's where the complex goes. When the ligand comes off, it will come off as acetyl iodide. And so acetyl iodide will now react here with water, and it'll produce acetic acid, which is our desired product that we've been aiming for. I also want to note here that when acetyl iodide reacts with water, it will produce acetic acid, and it'll also produce hydroiodide, which will then also react with methanol again to produce methyl iodide, which will also go to that first step again in the oxidative addition. So just to recap, the iodine here will migrate and cause the reductive elimination to produce the acetyl iodide, which will then react with water, produce acetic acid. And so there you have it. That's the entire catalytic cycle of the Monsanto process. We have the initial structure here at A. It goes over here and the methyl iodide is added via oxidative addition, both of them in transposition. We have a methyl group migration and carbonyl group insertion, and then we have a reductive elimination to produce methyl acetic iodide. Sorry, and that acetic iodide, once it's taken off via reductive elimination, reacts with water to produce acetic acid, and uh, in this process, the catalyst is then reused and reused again and again in this process of making acetic acid. Now I'm going to talk about the turnover frequency. Turnover frequency refers to how many times the catalytic cycle occurs on a single site per unit time. So through my research, I have discovered that the Monsanto process had a TOF turnover frequency of 450 hours to the minus one. A different catalyst I found that utilizes hydrogen and carbon dioxide as a reactant to produce acetic acid. This is a rhodium complex with four acyl groups with two bridging bonds. And in this cycle, the TOF has a value of 30.8 hours to minus one, significantly less. So this sort of highlights and reinforces how efficient the Monsanto catalyst is in producing acetic acid. I also want to talk about the rate determining step. And so in this Monsanto process, the rate determining step is the oxidative addition step, which I also have here again as a visual aid. The speed of this reaction it basically depends on the rate at which this methyl iodide is oxidatively added to the complex. So to speed up this reaction, a lot of methyl iodide is actually added to speed it up. And this can have some pretty dire consequences, which I'm going to get to shortly. So so what with all this, right? So um, actually, the Monsanto process is an extremely important process, as it accounts for roughly about 60% of the acetic acid production around the world. Acetic acid is important because it's used in many applications, from food preservatives and additives to ink for textile printing, pharmaceuticals, pesticides, and acetic acid itself is even used for a precursor for many other molecules being synthesized. So this is a pretty important process, this Monsanto process. So what are the pros and cons here? What are the advantages and disadvantages of the Monsanto process? So first, I want to talk about the advantages of the Monsanto process in the catalytic cycle. First, it has a really high yield with only very mild conditions. Monsanto process gives a yield of 95% acetic acid while consuming up to 99% of the methanol and 85% of the carbonyl that's put into the system, which is very good. And to get this yield, a temperature of only 180 degrees and 220 degrees Celsius required, and only a pressure of 30 to 40 atmospheres. Previous catalyst cycles before the Monsanto process came around included nickel, mercury, cobalt for the metal centers, but these resulted in higher environmental damages, lower yields, and more byproducts. In terms of the environmental impact of rhodium, it can almost be considered zero or nil because it is so rare and hard to find that you would never actually get a lot of rhodium ever in one spot at a given time, even in an industry setting. And this shows how effective rhodium can be at such low quantities. So I also want to talk about the three disadvantages to the rhodium complex, the Monsanto process. The first one is that this is the catalyst in a homogeneous catalyst, and that requires a lot of energy to separate from the reactivity media. Also, the presence of the Higg-like-containing compounds such as the methyl iodide could cause a lot of corrosion to equipment being used, especially when an excess amount of methyl iodide is being put in to drive the reaction forward because of that rate limiting step. The second disadvantage I want to talk about is that the Monsanto process requires a lot of water, about 14 to 15% by weight. So to ensure the stability of the catalyst, having all that excess water requires a lot of complicated purification steps to extract the product acetic acid and to sort of take out the water and to also extract the catalyst. So this excess water can sort of cause a lot of byproducts. And it can cause byproducts due to the water gas shift reaction, which I have highlighted here. Essentially, any water that is not needed for the catalytic cycle, they can potentially react with carbon monoxide, produce hydrogen and carbon dioxide. and this is very highly likely given the intense conditions that this catalyst cycles is in. Lastly here, the third disadvantage here is that rhodium is just stinking expensive. It's very scarce transition metal, and it can be anywhere up to $30,000 to $100,000 depending on how much you're buying, which is a lot of money. And because of the complicated purification steps needed, it could very easily lose a little bit of that catalyst, and just losing that a little bit can be devastating because it's expensive, and it could just end because it's the high cost value. So lastly here, I want to end off bringing up an alternative method to this complex. Is iridium the way of the future when it comes to acetic acid production? Iridium can basically replace rhodium in the catalyst cycle. The entire cycle pretty much stays the same, except the only difference is that iridium is replacing rhodium in the metal center. Back in the 1990s, iridium costed significantly less than rhodium, and although it is getting close to being just as expensive now, it's still cheaper than rhodium. Iridium as a catalyst uses 8% less weight by water than the rhodium catalyst, which uses 13 to 15% by water. And the rate determining step with iridium is different, and so you'll be able to use less amounts of methyl iodine in in the iridium's catalyst cycle. So that means that if iridium was used, uh, less purification steps would be necessary, and there would be a less likelihood of corrosion on that machinery as well. The only downside with iridium is that it requires more of the base catalyst to work just as effective. But over time, if we can make the iridium catalyst work with different promoters and aids to a cycle, it might be able to become more efficient than rhodium catalyst. Time will tell, as the most cost-efficient catalyst is always being brought forth into the industry. Oops. Those are my references. And yeah, I want to thank you all for watching and listening. I hope you guys learned a little bit about the Monsanto process and the production of acetic acid.